Welcome back to the Foundry by Forge College. I am so excited to jump into today's explainer. We're going to be looking at a real engineering blueprint for building secure, mechanical smart contract vaults, specifically focusing on implementing robust withdrawal functions. Now listen, if you've ever felt that sudden knot in your stomach when you're writing code that literally handles other people's money, yeah, you were definitely in the right place. We're going to break this whole thing down into a completely foolproof mechanical process. So just to recap, in our previous lesson, we were busy applying performance monitoring to pre-deployment checks, right? We were measuring, analyzing, and really mapping out our gas usage and all that good stuff. But now, now it's time to actually take those blueprints and build the machine itself. We're moving out of that theoretical design phase and stepping right onto the factory floor to assemble a withdrawal mechanism that's just as safe as it is completely transparent. Okay, let's dive into this schematic overview real quick. First, we'll cover the anatomy of a secure vault. Then, checks, effects, and interactions. After that, defeating the reentrancy heist, followed by audit logs and intent, and we'll wrap up the whole shebang with safe fails and testing. All right, let's get to turning some wrenches. Part 1. Anatomy of a secure vault. Engineering trust. Let's be honest for a second. Writing code that holds actual, real-world value, it is inherently stressful. It's not just a regular Tuesday at the keyboard. It kind of feels more like diffusing a tiny digital bomb, right? But hey, we can totally eliminate that stress by engineering a mechanical system that doesn't just rely on blind hope, but instead on a highly predictable sequence. And the absolute foundation of this vault is a concept called checks, effects, interactions, or CEI for short. Think of it exactly like an old-school vending machine. When you want to buy a candy bar, what happens? First, the machine checks if you actually put in enough money. That is your check. Then it deducts that amount from your internal credit. That's the effect. And only after your balance is reduced, it physically drops the candy bar right into your hands. That physical drop, that's the interaction. Imagine if it dropped the candy before deducting your balance. You could just yank the plug out of the wall and get free candy forever. Well, guess what? We apply that exact same logic to our smart contracts. So here is the absolute golden rule, written right out on our blueprint. Update the contract's internal state first, then perform the external call. This is basically the core of our patent design today. By updating the internal ledger first, we're guaranteeing that even if some fast-handed digital thief tries to grab the cash and somehow cancel the transaction or trick the system into running twice, their ledger balance has already been reduced to zero. There's literally no way to double dip because our internal paperwork is already finished. Moving right along to Section 2, checks, effects, and interactions. The gears in motion. Let's see how this builds out in practice. All right, let's look at the exact mechanical sequence required in our Solidity code. These are the 5 turning gears of our auditable vault. First up, we store the user's current balance, their balance before, just so we have a solid record of it. Second, we use require statements to check that they actually have the funds to withdraw. Number 3, and pay attention because this is absolutely crucial, we deduct the balance. The internal ledger gets updated right then and there. Fourth, we emit an intent log, which is basically like printing a receipt saying, hey, user X is about to withdraw Y amount. And finally, step 5, we execute the external call to actually send out the ether. In all the advanced learning programs we run at Forge College, getting this exact 5-step sequence hardwired into your muscle memory is treated as an absolute necessity. Which brings us to Section 3, defeating the reentrancy heist, locking the doors. So what happens when someone actively tries to break our beautiful machine? Well, that brings us to reentrancy. Honestly, it sounds like some catastrophic world-ending bug, but really, it's just a known stress test that our machine has to be built to handle gracefully. And this brilliantly illustrates the exact difference between a vault that gets robbed blind and a vault that stays totally secure. Take a look at a naive withdrawal. It does the interaction first, it sends the money, and then it tries to update the ledger. A malicious contract can easily interrupt that process, receive the money, and then call the withdraw function again before the ledger ever updates. Boom, the contract is drained. But a robust withdrawal uses that state-first method we talked about. Because the effect happens first, a reentrancy attack just hits a ledger that already reads 0. Nice try, right? Now, just to add a pair of suspenders to our belt, we also use the non-reentrant modifier. It's a staple concept we teach in Forge College's advanced Solidity courses to prevent double spend behavior. Think of this modifier as a really lightweight emergency brake, or like a physical deadbolt on a door. It essentially tells the system, hey, while this function is running, the door is locked tight. Nobody, not even the person currently inside, can re-enter this specific room until the entire process is totally finished.
It completely shuts down any funny business.
Onward to Section 4, Audit Logs and Intent, Tracing the Steps. Okay, so now that the doors are locked and the money is completely safe, we still need to track it. Because a truly secure vault isn't just about stopping thieves. It's about knowing exactly what happened inside, at what exact time, and by whom. Notice how we break down the transaction lifecycle here, exactly like a mechanical receipt tape, using 3 absolutely crucial audit events. First up, withdrawal requested, which acts as our statement of intent. Second, withdrawal completed, representing our happy success state. And third, withdrawal failed, for when, things just don't go as planned. By emitting these events at very specific moments, literally anyone looking at the blockchain can trace the exact flow of the transaction.
But wait a second, what if the external call actually fails? What if the recipient contract straight up rejects the ether? Well, for that, we use what's called a compensating action. Instead of just throwing an opaque, super confusing transaction revert, where the whole thing just blows up and leaves absolutely no trace behind, we hit the emergency brakes gracefully. We manually restore the user's balance back to exactly what it was before, and we emit that withdrawal failed event with a specific reason attached. Now, this is a deliberate design trade-off. It keeps the transaction right there on the ledger, so we have a perfectly recorded failure that we can actually diagnose later, rather than just getting some silent, unhelpful error.
Almost at the finish line. Section 5, Safe Fails and Testing, Quality Assurance. It's never enough to just build the machine. We have to run it through serious quality assurance to validate both our happy paths and our failure paths. So the crucial point is right here in this final patent diagram checklist. We need to make sure state and events align perfectly. For a successful transfer, we expect to see the requested event followed immediately by the completed event, and obviously the balance decreases. If the transfer fails, well, we should see requested followed by failed, and that balance gets restored to its original amount. And if someone attempts a sneaky reentrancy attack or guard blocks it, we only see the initial events, and that balance remains safely unchanged. If your local tests match this grid right here, your vault is rock solid. We have really built an incredible machine today, guys. But I want to leave you with this provocative thought to chew on. Your vault is secure. Your tests are completely green, but how are you going to debug it when a real user's transaction mysteriously fails out there in the wild? Having audit logs is one thing, for sure, but knowing how to actually read them, that's a whole different ballgame. And that perfectly sets up our next lesson on debugging withdrawals and audit traces, where we're going to put on our trench coats and become blockchain detectives. And that wraps up today's explainer on implementing robust withdrawal functions. I really hope you're feeling much more confident about turning all these theoretical security patterns into concrete, testable code. To dive deeper into the subject, access our full capstone projects, and really master Web3 development, make sure you head over to forge.college. We've got an amazing community over there just waiting to help you build safer, better smart contracts. Thank you so much for joining me today, and as always, keep building.